So I'm honored now to introduce Auke, my colleague from Switzerland. And this is actually the first time that he's participating in this workshop. And when we look at his background, we see a wide range of knowledge that he brings into this in our workshop. He studied physics in his bachelor's and master's, but he did a PhD in artificial intelligence in Edinburgh. And he's now the head of the biorobotics laboratory. And as you can hear from the name, he's working a lot with biologically inspired robotics, but all of that also goes back to the computational neuroscience behind it. And I'm looking forward to see his presentation today. Thank you, Auke.
Great. Yeah, thanks a lot, Marco. Is the sound good? Everybody hears me?
And yes, I can hear you. I can see your slide. It looks perfect.
Yeah. So so thanks a lot for the invitation. It's a super exciting workshop, and I feel a bit sorry I cannot attend the whole thing for family reasons, but what I heard so far is super exciting. And what I'll try to contribute is a bit of view related to neuroscience, what happens a bit behind in the circuits in animals. So I'll briefly cover what we do in modeling lower vertebrates using robots and models. Super rapidly about human models as well. And then I changed from abstract. I thought maybe to show a bit what we did on paleontology robotics. And normally everything should be in 16, 17 minutes. So I hope I'll be in time. So what I love in robotics is indeed this feedback loop between biology and robotics. And obviously for me, it seems it's worth taking inspiration from biology to do field robotics. I think we all agree. But I really love this topic of using a robot as a physical model and to test some hypotheses in neuroscience and in hydrodynamics and paleontology. So today I'll cover with these two topics. I think every neuroscientist should collaborate with roboticists, and now also paleontologists should to do good science. And I love the use of robots for that. And the reason I like that roboticists look at neuroscience is because locomotion being this interaction of so many components and being such a beautiful phenomena, but at the same time so complex, I really think it's worth to take a robotics point of view to try to reverse engineer what's happening. And here, for instance, just steady state locomotion is beautiful in animals. And for me, it's really beautiful how the nervous system solves this so well. Even more impressive is all these agility dog competitions, which are really beautiful, where in this case, it's not steady state locomotion, far from it. And you have all these multimodal sensory inputs coming to the system. And it's really beautiful how dogs are able to do this highly agile motor behaviors. So for me, at the first level of approximation, there are four main components here. First is the clever mechanics, the musculoskeletal system, which is well designed to do locomotion, obviously. And then in vertebrate animals, you have the spinal cord that's really very sophisticated for locomotion control, with, as you know, many reflexes, and this beautiful concept of feed-forward controller, central pattern generators, which are these distributed neural networks, which by themselves can produce oscillatory pattern for locomotion. And finally, you have all the high part of the brain that are very much necessary for modulating the gaits, especially in the second video. The second video really has highly dynamic changes from descending modulation, whereas the first video probably has only a single drive being sent to the spinal cord, and then it's the spinal cord that's really in charge. But in any case, the spinal cord is super, super important and often a bit underestimated, even in neuroscience. So sometimes people underestimate to what extent the spinal cord already solves the locomotion control problem. And finally, I really love this analogy of Jerry Lubb, who sees the spinal cord like a puppet on strings, where a finite set of descending pathways can modulate a whole range of movements and really simplify planning and learning, because you lower down the space of communication between higher parts of the brain and the spinal cord. But this is really a first approximation, of course, and the complexity are in the details. How all these components interact are still very far from being known in neuroscience. And here I think that models can help to decode the respective role of these different components, and possibly also how they have changed during evolution. And one hypothesis that I have is that lower vertebrates are extensively driven by CPGs, the feed-forward neural oscillators. And the more you go to mammals, the more you are based on reflexes and on modulation, descending modulation. But to test this hypothesis, you need models. So that's what we do. We make numerical models of the spinal cord, and we couple them in closed loop with either mechanical simulation of the body or with real robots, such as to have real physics. So very rapidly, I'll show a bit what we do, what we did, and what we're doing on the Salamander. Then briefly also what we do on human locomotion. So as you might know, I have shown this to many of you, so sorry if you have already seen this, but I still love salamanders because they're so important from an evolution point of view, because essentially all terrestrial tetrapods, mammals included, are obviously evolved from a salamander-like ancestor. So I think it's a very key animal to study this transition from swimming to walking during vertebrate evolution. So what we did together with neuroscientists is to see how a swimming circuit could have been modified during evolution to get new layers to control the limbs, and how such a system can do switches between gaits in the salamander. And something which is very impressive is that if you electrically stimulate the spinal cord of a salamander, you can have automatic switches between walking and swimming, as you'll see in a video just later. So for this, we have a whole range of models, but often the simplest ones are already pretty good, using coupled oscillator models. So really very abstract, very close to robotics controller, in fact, very easy to implement in real time, and still interesting to address scientific questions. So some of you may have seen, many of you may have seen this video, but I still like to show it because for me it's a very nice demonstration how beautiful central pattern generator circuits can modulate locomotion, at least in principle. So what you see here is our Salamander robot driven by our coupled oscillator models that are programmed on board of the robot. And the only thing we send remotely with a remote control are the descending activation that represent what high part of the brain would send to the spinal cord. And by playing with just these two signals, we have control of speed. So the more we stimulate, the faster the speed. If we pass a threshold, we switch to swimming, exactly what happens also in the real animal. And if we stimulate more one side or the other, we have control of speed. So for me, a CPG is therefore beautiful as a way of modulating actively not only one type of locomotion, but even switching between types of locomotion, and really simplifying the controls such that high part of the brain do not need to worry about every single muscle. But obviously, this is just part of the story. And one thing we do actively now is close the loop with sensory feedback. Before I show that, I just want to highlight we even can distribute this controller in local elements. So we can make these creepy videos where we have a robot splitting in different parts, because like the distributed control, the spinal cord, we can make local oscillators controlling the local modules. So nowadays, a big topic in my lab is to see how sensory feedback also plays a role. Obviously, animals have not only CPGs, but they have sensory feedback. And it's a big debate for quite some time, in fact, in neuroscience, how locomotion is generated in animals. Is it more due to a chain of reflexes, like Sherrington had proposed? Or is it more due to a feed-forward mechanism with half centers, namely neural oscillators, that drive muscles and then drive the limbs? I don't have time to go in details, but I really recommend for this discussion that you read this paper of Art Kuo, who very nicely explore how to create limit cycles with these two extremes. And in terms of neuroscience, it's really a question of, is it more the peripheral nervous system or the central nervous system that's responsible for locomotion? And in terms of control, is it feedback or feed-forward control? Obviously, in animals, it's both, by the way, it's obvious, but I think the debate is kind of settled now, but at some point, there are really almost battles between these two camps in neuroscience. So now, to model this, you need bodies, of course, and that's where robotics, I think, has to contribute, because robotics, we know how to make physical models, We even know how to make passive walkers, like this beautiful work of Steve Collins, Martijn Visse, and Andy Runa. And so we know that a well-designed mechanical system can already have locomotion properties. Similarly for swimming, by the way, if you look at the trout swimming here in Van Carmen Street of Vortices, you have this trout swimming, benefiting from the vortices. And it happens to be a dead trout. So it's really purely a passive mechanical system that benefits from the environment. So the body mechanics are clearly super important. So what we're currently exploring is how sensory feedback plays a role in shaping all these locomotion patterns we have seen. And this is a nice project we are doing now with Akio Ishiguro and Emily Standen. And what's exciting is we don't only look at salamanders, we also look at walking fish like Polypterus. They can walk and they can swim. And centipedes, which are super cool. Some of them are amphibious that can both swim and walk and show a very interesting transition, very similar to the salamander. So a current hypothesis, it could be that some of the phenomena that we see could be similar between these animals and very much sensory driven. So really dynamically changing which part of the body swims, which part of the body walks, depending on local feedback and especially pressure from the water. I don't have time to go in details, but the idea is that sensory feedback is not only there to handle perturbation, which is the obvious goal of sensory feedback. And it's easy to show that if you open loop, like on the left, you cannot handle perturbations. If you close the loop, for instance, with stretch reflex, stretch feedback, you can. So that's the first obvious role of sensory feedback. But what we're currently finding is that sensory feedback also could possibly replace direct coupling between oscillators to generate patterns. And this is very nice work from Akio Ishiguro group, where you can get very similar gates to what we had before, but in this case with neural oscillators, which have no communication between elements, but just communicate interactively through the physics and through sensing feedback. And I don't have time to cover that. We also show this for swimming. We have a paper under review that shows that swimming as well can really benefit from local feedback loops. And it's surprising to what extent it could, in principle, even replace direct coupling. So really, it's kind of a redundant mechanism for generating patterns between feed-forward driven due to CPG and feedback driven due to sensory feedback. And I recommend that you check this paper on the right on scientific robots, which has a similar model for centipedes in simulation, which is very cool. Okay, so to summarize, while I was a CPG person, I'm now going more and more into closing the loop with sensory feedback, seeing that there is a beautiful kind of redundancy between CPG-driven mechanism and local feedback mechanism, and finding that this local feedback can really help to synchronize oscillators, sometimes even generate rhythms. I didn't have time to cover that. And therefore, since you have multiple principles in parallel, it's really self-organized locomotion, where the biomechanics also plays a big role. And I think there's a good reason for this. It makes the whole system very robust against perturbation. So it really helps if you make lesions in systems, if you remove some sensing. If you have both the CPGs and the feedback, you can be very robust against lesions. Okay, so that covers a bit on the salamander work. So let me very rapidly show, I won't skip it because I think I'm a bit late, but there's still a debate in the neuroscience community if there are roles or not of CPGs. And we believe there is, and we have a good review paper that kind of covers the indirect evidence for this. But interestingly, people like Hartmut Geyer and Hugh Hare have shown that you could in principle be sensory driven and have beautiful locomotion. So we were a bit frustrated by that. It's a beautiful paper, but since I love CPGs, we're wondering what could be the benefits of CPGs on top of sensory driven signals. And here it looks like at least one contribution of a CPG would be to simplify the control of speed. So we find out that if you add to Hartmut-Gay's model a CPG, you can really nicely control speed by just the control of frequency. And especially if you place it at the hip, at the most proximal joints, you can add speed control on the sensory-driven system, which otherwise is very, very hard to control in speed. So that's a bit the current view in humans, is CPG has a less role than in lower vertebrates, but at least it's useful for speed modulation. So I just passed this. So now, last, I think 3 minutes, I still hope I'm in time. I want to cover a bit more what we do on amphibious robotics and paleontology robotics. Because here, there was for me a very cool project. Like John Yakatura at the bottom, he approached us, he knew we were making Salamander robots, and he asked us, could we help? Because he had access to a very well-preserved fossil, of which he had the full morphology. He also had access to the footprints, fossilized footprints of the same species. And clearly that leads to a very interesting question. What was the most likely gait of this extinct animal? And John did an incredible work at very systematically exploring the kinematics and EMGs and dynamics of modern animals, and take body plans that are kind of a bit around the body plan of this old extinct animal. And a big contribution, in fact, of the paper was to very systematically characterize several quantitative properties of sprawling gaits, like what is the body height of the animal, how much does the animal use a spine or not, so that's the second axis here. And the third axis here is how much the animal use the first degree of freedom in the chain of the limbs, or the second degree of freedom. And interestingly, depending on the animals, you see several different characteristics. So it's very useful to place modern animal in what we call this sprawling gait space. What we did was then make a robot that approximates the fossil that had been CD scanned, and using inverse kinematics controller, very systematically generate many gaits that populate this sprawling gait space. And all of these gaits walk in the footprints left by the animal, but have different properties like the body height that I mentioned, the amount of spine bending, as you see in the middle, or the amount of long axis rotation versus humeral retraction. And what we found is basically a whole series of gaits that the animal in principle could have used. But then on top of that, by using matrix to quantify the power expenditure, the quality of the balance, the quality of the precision in the footprints, we could little by little give scores of likelihood of these gaits. And if you combine all these matrix, we kind of zoom in what we feel was the most likely gait used by that animal. And these are the data points that you find here. So in principle, the animal could have used many gaits. They're all valid. They match the morphology, they match the footprints. The most likely gaits are quite erect, as you see here. And there was a bit of surprise for the paleontologists because it comes closer to the caiman, which is a much more modern animal than the orobates. And here is what we believe was the gait of that animal. So you see the simulation on top and the robot on the bottom. And we also apply the gait to the kinematics simulation. So here's the CT scan of the bones that we could then actuate. And for us, it was very exciting to relive this extinct animal and see what were the possible gaits of this animal. So to conclude, last slide. For us, it was very exciting to find this large diversity of gaits that the animal could have used. It's not too surprising, it's highly redundant. And then find out with this exclusion approach, with a matrix, which was the most likely gait for us. And it's a quite erect gait, quite athletic, closer to the caiman than to the salamander. And more generally, I really find this exciting. I'm not sure if we have new projects like this, but I would love to do it again because it's really nice to have a very quantitative way of doing paleontology. And I feel that robotics, the methodology of robotics can really help explore these scientific questions. So for me, it was super exciting. Okay, that's it. So thanks for attending. If you want to see the videos or get the papers, just type biorobot EPFL. And here I'd like to thank the people and the funding that has made this possible. Great. So thanks a lot. Sorry for if I was a bit over time. I hope it was within time.
No, it's perfect. Very cool work. And I would like to maybe make a comment on your first introductory statement where you say every neuroscientist should work together with a robotics engineer. Maybe also every robotics engineer should work along with a neuroscientist. Yes.
Yeah, I agree. I agree. I think for me, these collaborations I have with neuroscience is super cool because they bring new insights, new ideas, and for them, they find it also quite exciting to see the robots move and the models move. They learn also a lot with making a synthetic approach basically to science. Yeah.
So is it correct to say that if you have a proper design of your feed-forward signals, you can be less accurate with feedback control, maybe?
Yes, yeah, and the feedback also animals have delays, so bigger delays, much bigger delays than robots. So they are a bit maybe more noisy, like sensor properties will change over time. There are more delays. So that's, I think, also one reason why the feed-forward control has a big role in all animals, including in humans, but possibly a bit less than in lower vertebrates, but completely. Yeah, I agree. Yeah.
And I have a question to the last work you presented. In order to evaluate what the most likely gait was, you use a metric. That was more designed by a human intuition in the end. Do you think there could be also still the possibility of a different gait, or how likely do you, in percentage, what would you say, how likely was it that it was the gait that you presented?
That's a very good question. So that's why everything we have a big database and a big simulation and the whole data is there so that people can play with the matrix. So you can remove some matrix. In principle, if we collaborate, we could add matrix. So since we didn't know exactly, we want to leave people open to play with the matrix. So for sure, you can at least remove some matrix, set them to 0, and you'll see new gates appear, or at least new ones become likely. And that's why I think the methodology is almost more important than the results, because I completely agree with you. Maybe other matrix will be more interesting in the future. Maybe we have missed some. So that would be cool to explore new matrix. Absolutely.
And what's the next distinct animal that you're trying to bring back to life?
Yeah, some people, it's a bit secret, but some people approach me a bit for all the animals. So maybe that will happen in the future. And if people want to collaborate, have ideas, I would love to. But and one thing which will be cool, I know that Akio Ishiguro wants to explore all these incredible morphologies which have disappeared when we had all these amazing animals at some point. That would be cool to relive, yeah, make them alive again.
Yeah, and there was a question on YouTube asking about the spine. Do you think it's something we should add to our quadrupeds? Nowadays, you see most of the quadrupeds are quite stiff when it comes to their torsos.
Yeah. Well, interestingly, we tried at some point to make our own robots like Cheetah Cub. We tried to add a spine, and it was very hard. I know that Sangbei, I'm not sure if he's listening, but I know at some point he had a spine in the MIT Cheetah and then removed it. On one hand, it's super cool, but on the other hand, it's very hard to control and use properly. So it's a trade-off. But for sure, for turning, for increasing stride lengths, there are many benefits. If you see the dog agility competition, the spine is used a lot. So it would be beneficial, but hard to control.
Yeah. And then there's another question in the chat. Do you think skin is the most important sensory organ presented all over animal or human's body and contributing to locomotion, which is missing in robots we make?
Absolutely. This I don't know who wrote that, but if somebody could give us sensitive skin that's amphibious, I would be the first one to jump on it. So I completely agree with that statement. For me, skin, tactile information that with pressure, shear force, water pressure, I would love to have that. So that would be, and I sure if you take a snake, it uses that information so much. It's really missing. Absolutely, yeah.
Then we come back to feedback control again. Yeah, to use
Yeah,
that
yeah, of course.
information.
Yeah, absolutely. Yeah.
Then maybe by Dimitrios. Maybe Dimitrios, you can ask it also.
No, very quickly, can you distinguish between walking and running based on the footprints of the?
That's a very good question. So it's a walking gait, so high duty factor. There don't seem to be a flight phase for sure. And based on what we know from modern animals, the duty factor, but that's a very good point because we had to estimate it. We tried with several, and I think the final duty factor we have is 75%, so quite slow gait. But that's interesting. It's still an open button, the duty factor. Yeah.
And then there is the last question before we continue. Do you think salamander-like animals take advantage of their spine more than their legs during locomotion?
People have looked at that. So first of all, there's still a big proportion coming from limbs, and sometimes the spine seems straight. For high speed, yes. For low speeds, maybe not that much. For sure, it's very easy to show that you optimize stride length in this sprawling posture. Like we computed like at least 40% high speed thanks to spine motion. But still, the benefits has to be a bit explored.
Okay, thank you. So I think we have to continue with our program. Thank you, Auke, again.
Thanks a lot for the great questions. Yeah.
Thank you.